Okay, hello everyone. Um, yeah, so I think today I would like to wrap up everything for this semester, and so that you can, just focus on the final project and um, finish your final several things to finish this semester, right? I give you some time later, so to discuss our problem. Before I start, I would like to mention several things. One is a midterm. I have already posted the score in the Blackboard. Please let me know if you have any question, so we can discuss your grading. But generally speaking, I think most of the students have a very good score for the midterm. So sorry, again, sorry for the delay, but your midterm score has been already posted. And another thing is that because of the this semester, it's not very easy and fair to count the attendance. So I decided to give every student a full attendance score, so you can count the attendance score directly without any discount. Okay, and the final is about the final project. So try to start as early as possible. And let me know if you have any question using the GPU or the cluster. Okay. Then I think that's it for this semester, right? Today I think let's just finish some remaining contents in the GPU section, and we can quickly wrap up everything regarding the GPU and give you some idea how to implement on the GPU for the DGEMM, okay, metric application. So I remember last week we mentioned something here, right? Something for the memory coalescing. You still remember? So the best case or the optimal case is you ask all the threads to access the aligned memory access. For example, you should ask 32 threads in a warp to access the memory space from 128 to 256, right? So but this case, you don't know when the start point of your memory address, but try to be, for example, sometimes this situation could happen, right? But it's okay because it's still aligned memory access, but try to avoid this case, right? So ask all the threads to access to the same memory location. And this is not also not a good case, right? You ask one thread to access not continuous memory address, right? So the key idea of the memory coalescing is to ask all the threads to access the continuous memory locations. So that's the idea. For example, you have the 32 threads in a warp. You ask the 32 threads to access 32 times 4, right? Each transaction could be 4 bytes, right? To ask them access the continuous memory locations. Okay, so here are some trick. You play with the structure of array or array of structure. Okay, and so the next thing is shared memory. So what we have mentioned here, this is for global memory. So pay attention to that. So we access the data in the global memory. Okay, so I remember I mentioned what is a global memory and what is a shared memory. So generally speaking, the global memory can be accessed by all the streaming multiprocessor, right? But the shared memory is only owned by one streaming multiprocessor. So that's the main difference. If you look at our previous high-level architecture figure, right, of a GPU. So for that big figure, we have a multiple streaming multiprocessor, and each multiprocessor will have their own shared memory. But for global memory, all the streaming multiprocessors share the global memory. Okay. So here, what we mentioned for the memory coalescing is for the global memory. Okay. So next thing is for the shared memory. We also need to maintain a good usage of the shared memory. So shared memory is a very fast memory located in each streaming multiprocessor SM. Okay, and it's the same hardware as a L1 cache. So we will be discussed later, right? So L1 cache and the shared memory can be configured to each other. So what does this mean? For example, we will, for the V100, we will have 96 KB shared memory plus L1 cache. So that means you can use 48 shared memory, 48 L1 cache, or you can configure all the capacity to the shared memory, right? 96 of the shared memory. So but this can be talked about later. So for example, here, maximum size of shared memory is 84. Or 48, sorry, it's 48. But just as mentioned, it can be changed later, right? So it can be configured. Okay, the scope of the shared memory is a block. Please remember here, streaming multiprocessor is SM. SM is not equal to shared memory, right? So if in the future people mention the SM, you should notice that this is for the streaming multiprocessor, is not for the shared memory. Okay, so this is the notation for the streaming multiprocessor, it's not for shared memory. Okay, so how we can utilize the shared memory, right? What is the shared memory syntax? So I think this is important because in the final project, how you can implement a but kind of efficient matrix application is to use shared memory. I will quickly mention it today. Okay, but if you just use a global memory to program OpenMP style code, that's not an efficient version, right? And maybe your code cannot work. So you have to use the shared memory carefully and smartly. So how we can define a shared memory? So we can allocate a shared memory statically, okay, or dynamically. But you, generally speaking, for your final project, statically allocating the shared memory is enough for you, okay? So how we can statically allocate the shared memory? So we just put this shared syntax here and float data. This is a size, okay? So this is you need to declare this variable or shared the variable in the shared memory in the kernel, right? So this is nothing related to host code. I still remember for the host code and device code, right? So this is how we launch the kernel from host. And in the kernel, you can define as a shared memory variable like this way if you want to use the dynamic allocation format or syntax. Okay, but generally speaking, the static allocation syntax should be enough for you to finish your final project. Okay, this is kind of the similar to the dynamic allocation and the static allocation. So I received several emails from multiple students previously regarding, okay, they just want to allocate a very large static variable, then segmentation fault happen, right? So that's a truth. That's a truth, right? So if you want to allocate a very large memory, no matter for C or C++, you need to use a dynamic allocation. But for the GPU, I don't think the idea is the same. For the GPU, yeah, I mean, it's kind of same, right? So you want to control the size of the shared memory also dynamically, right? But there is also any other benefit from the shared, from the dynamic allocation. For example, as I mentioned, if you want to use all of the 96 KB shared memory, you cannot just allocate in the kernel, right? You have to use a dynamic allocation. So here are some other details about dynamic allocation, so you can check the link here. Okay, so I just want to quickly give you some idea how we can use the shared memory. So for the shared memory, the general idea is that you have to create a shared memory variable, and you ask each thread to work on each piece of the data in the shared memory. And after that, you need to have the thread synchronization here. Okay, so for example, I can create a scratch variable and ask each thread to work for the different, this is just a copy, right? It's just a memory copy, right? You have to copy something back and forth between begin variable and the scratch variable. So after that, you need to synchronize. So here you need to manually synchronize the threads. Otherwise, it will have some bad thing happen or unexpected thing happen. So here is a thing I want to mention. So for the different GPU kernel, after you finish each kernel execution, the synchronization would be happened automatically, right? As we mentioned previously in previous slides. But for the shared memory, every time you finish a batch of the execution, no matter copy or the calculation, you have to use a synchronization here. So I will give, I believe I give some example code in the final project, and you only need to fill out some kernel things, right? And you can notice that I put some synchronization here to make sure that all the thread would be in the same status after a batch of the computation. Okay, and the shared memory is faster than L1 cache, slower than register file. It's relatively small. So for example, it's only about several tens of KB, right? So a shared memory application. So this is a very classic shared memory application. So we usually call it histogramming, right? You count the byte frequency for each symbol. So here, I mean, for example, you have the different symbol A, B, C, D, E, F, G, right? You have the 26 letters, and you want to count the frequency of each symbol. So how should you do that? So here, if you count the byte, we have the 256 element array, right? How we can count the frequency. So the original naive version is that you can build output in global memory. You have n global stores. But the smarter idea is you can build output in shared memory and copy the data to global memory at the end. And you only have 256 global stores. So I think maybe there is no code here, right? Okay, so the idea is that, for example, as I mentioned, let's just talk about 26 letters, right? So if you have 26 letters, you don't need to fully utilize the global memory. You can copy part of the data into the shared memory and count the frequency. After that, you can copy the partial frequency back to the global memory. So that's kind of like a caching mechanism, right? You partially copy some data and operate in the shared memory, and finally you just copy the result back to the global memory, right? And you can multiple reuse the data in the shared memory. Okay, so that's the key for the metric matching application. I will show it later. So here, something we mentioned before is the computation intensity, right? For the matrix matching application, the intensity is n. For the other application, it could be y, it could be between y and n. So that's why we needed to use the shared memory, because if one data could be used multiple times. So this is the whole idea through our HPC class, the data reuse, right? So in the beginning of this semester, we mentioned how to reuse the register, how to reuse the cache. Here is the same thing. If you can reuse the cache, and also maybe you can reuse not reuse, but you can use the shared memory, right? In the shared memory, you can reuse the data for multiple times. So that's the general idea. Okay, a common patterns in the kernel. So you copy the data from global memory to shared memory, and you do the synchronization because you initiate the shared memory, right? And you can perform the computation, and you can incrementally storing the output to shared memory and make a synchronization as necessary. And finally, you copy the output from shared memory to the output array in the global memory, right? So I will give you the matrix application example later. But the general idea is you break down your computation into multiple steps, right? Partial step can be finished in shared memory. After finish that, you just copy the data back to global memory. Okay, that's the key idea. So the final things for the shared memory is similar to the memory coalescing problem in global memory. Okay, so for the shared memory, we don't have a memory coalescing problem, but we have some similar alignment problem. We call it a bank conflicts. So shared memory is set up as a 32 banks. So if you divide the shared memory into 4-byte long elements, element I lies in bank I divided by 32, or mode 32. Okay, so a bank conflict occurs when two threads in a warp try to access the different elements in the same bank. The bank conflict is called serial memory access rather than parallel. So here is a very quick demonstration figure to help you understand what is a bank conflict, what is a bank conflict free. Okay, so here you can see that we, in the shared memory, for example, we have 32 threads, right, in a warp. If they just access to the different bank in the shared memory, that's fine. That's the bank conflict free. Okay, so for example, if you have 3 groups of thread, each group of thread try to access the same bank in the shared memory, then the access would be in sequential. That's exactly similar to warp divergence. So you can think about many principal design in the GPU are very similar, right? So they are trying to access to the different location to maximize the parallelism, right? But if they try to access to the same location, there will be a sequential execution. So similar to the warp divergence, right? So as I mentioned, it's very bad to have the warp divergence. So for example, if you have the if branch, right? So if the number of the thread or thread ID is even or if the odd, they execute the different part of the code, right? So that would cause some warp divergence. And the real execution for the warp divergence is you just execute the warp in sequential, right? So the first half of the thread just execute the first part, and the second part of the warp will execute another part. This is exactly similar to the bank conflict, right? So if the same group of the part group of the thread try to access the same bank location, then the execution would be sequential. Okay, that's very similar, but from the different angles. One is for the memory access, one is for the warp divergence, for the warp execution. Okay, and there is no divergence across warps. Okay, there is no penalty. For example, if you can control the different warps to execute on the different branch, there is no penalty. But for the 32 thread, right, that would be a penalty. So you can think about if I ask the first warp to execute the first branch, the second warp, for example, if I ask a thread from 0 to 31 to execute the first one, 32 to the 63 to execute the second one, that's fine. There is no warp divergence. But if you ask the thread 0 to 15 to execute the first one and 16 to 31st to execute the second one, there will be a warp divergence. Okay, so try to avoid. I mean, the high level idea is try to avoid if else branch. But if you must use that, think about how to ask different warps to execute. Okay, that's the general idea. So here are some global memory, local memory, shared memory. I ignore the registers because it's a little bit complicated for you to understand. I don't think you need it for the final project. If you want to be a GPU expert, you definitely need to understand the register. But generally speaking, we only need to know the global memory, local memory, and shared memory. Okay. And if we want to achieve the coalesce the global memory access, try to use the shared memory. Okay, and you need to try to avoid the memory, the shared memory bank conflict, and you try to avoid divergent branches. Okay, that's the general idea and a key point for the GPU programming. But I don't think your matrix application code will have some problem because for the memory, for the GPU DGEMM, the memory coalescing is perfect, and the bank conflict problem is not a problem, right? So you just align the memory access and computation very well. So that's why we start from the GPU matrix application. And here some L1 cache, L2 cache, L3 cache idea I don't want to mention here. But NVIDIA, as I mentioned, NVIDIA allows you to configure the shared memory size and the L1 cache size, right? You can assign different size between them. But generally speaking, both of them are very small. It's just like 96 KB for each stream multiprocessor, okay? So here's something we don't need to know, constant memory, something. Okay, and finally for this deck of slides, I want to mention some GPU parallel library. And for example, now people are using the TensorFlow or PyTorch or some software to execute the deep learning framework, right? But all the high-level code are based on the Python, but the backend efficient library are all based on C or C++ implement CUDA code, right? So that's now the library's idea is you want to trade off the efficiency and the productivity, right? Because you want people to use abstraction syntax, but you need to implement something in low level for the high efficiency, right? And we have a lot of GPU accelerated library, for example, FFT, sorting, reduction, scan, and the matrix application. Okay, and that's why I find in the final project I want you to try use the production level library, because that could help you to understand in the future, even if you are not a GPU developer, right? How you can call the GPU code, and how you integrate your GPU code into the different library, even in the future for the Python library, right? So here are some general description. And here is the thing mentioned here. So your code cannot be as fast as a production level code or library as NVIDIA provided, right? But it's still good to try to write your own matrix application, right? And compare with the production level library. But usually you will observe that the difference could be very, very large or not very small, right? And what is a BLAS? I think we mentioned the BLAS for several times in this semester. That's a general basic linear algebra subroutines, right? It gives you a very basic scalar, vector, and matrix operations. Okay, so generally speaking, we have the different corresponding cuBLAS function. So BLAS is a very not old-fashioned, but we can see it developed for many, many years ago for different CPU architecture. AMD, Intel put a lot of efforts there, right? But for the cuBLAS, all the function is corresponding to the original BLAS function or those subroutines, but just add some cuBLAS here, right? So you have the original SGEMM, but you can put the cuBLAS SGEMM, right? And if you check the NVIDIA website, you will know all the API, how to use the API. Okay, so I don't want to go into the details, but because the BLAS is very basic, and the cuBLAS is just a GPU version. There's not much fancy things here. Right? Originally, there are 3 levels in BLAS, right? Vector operation, vector matrix operation, and matrix operation. Right, and BLAS was written in Fortran and optimized, just as I mentioned, by a lot of vendors, okay, for the different architectures. And CUDA has its corresponding functions, right, like vector multiplication, okay, and anything that use heavy linear algebra computations can benefit from GPU acceleration. So as I mentioned, a lot of people are using the TensorFlow, are using the PyTorch. So the backend operation are all based on the BLAS. So if you execute your machine learning framework in CPU, then that would call the CPU BLAS, right? If you offload your computation to GPU, then it will call the GPU BLAS, right? So similar idea, right? So you can implement your GPU blast, not blast, GEMM, right? But you can also call the CUDA version, but also you can implement your CPU version, right? I can ask you to wrap up all your code into a library, and I can use that, other people can use that, right? So that's the general idea. Okay, cuBLAS excel in situation where you want to maximize your performance by batching multiple kernels using streams. So cuBLAS provide you a lot of tricks there. So they play with a different number of the threads, play different number of the block size. They just try to wrap up all the small matrix application into a large, batch, right? So there are a lot of tricks you can use that. But generally speaking, if you need the cuBLAS, if you need to accelerate the linear algebra operation, to consider cuBLAS, okay? Here are some notation things: single, S, D, double, C means single complex flow, Z means double precision complex. That's just a general some notation here. Also, one thing I want to mention here, so for half precision, so nowadays a lot of operations or algorithm can be based on the half precision, 16-bit. For example, so I just want to use machine learning or deep learning as another example. So for example, if you train a neural network, you train a machine learning model, because the robustness of the model, you don't need to use 16.4 or 32 full precision, right? And the cuBLAS or some other library provide you half precision, 16-bit. So 16-bit sometimes lose the accuracy and can accumulate the round of error, but for example, for machine learning model, it's enough because this is robust, right? But for some numerical simulation, for example, earthquake simulation or climate simulation, maybe half precision is not enough, right? So you should consider, this is just a trade-off between the accuracy and the performance, right? You can use a lower accuracy type to achieve a higher performance throughput. So definitely, I cannot say 62 or 32 has a double performance to the 64. Usually it's not double, right? But it can be 1.5 times faster than the double precision. So you use a lower precision to achieve higher performance. Okay, that's the general idea. So here are some BLAS function. I don't think you need to know all of them, right? Because if you want to know which function you want to execute, you just check the NVIDIA website. They provide every function you need, okay? Okay, so here is the thing, how to actually use cuBLAS. So I think now cuBLAS has a v2.h. So please remember to include the header file here. But I remember in the code, I'm not quite sure, but I should give you some header file and some basic outline of the code there, right? So if you include the cuBLAS v2 and link the library, just use L cuBLAS as I demonstrated before, right? You can use MVCC and with the compilation flag L cuBLAS and include the header file there. MVCC would just compile the code, right? You don't need to specify the detailed library paths because MVCC would know how to find this library, okay? So header file cuBLAS H and cuBLAS SV2 include the interface to the newest cuBLAS library API. So in the NVIDIA website, they will mention that for some functions, they will be only including cuBLAS v2. In some, they will be still in the cuBLAS H, right? But I think for most of the code, you can find in the cuBLAS v2 here. Okay, there is some other library like cuFFT, cuDNN. So I mean, CUDA try to develop every mathematical library in the GPU for acceleration, right? But the not the bad thing, but they because the NVIDIA is a commercial company, they don't want to open source their code, right? And if you want to have some open source code, for example, BLAS, you can try, or metric operation, you can try Magma, right, from the University of Tennessee, Knoxville. So they have the group to focus on developing open source GPU code, right? But for the NVIDIA, they don't want to open source. They just want you to use their library directly, similar to the FFT to DNN, right? CUDA is for deep learning. Okay. Here are some other details. I don't think you need to know that. And here is the array indexing. You should be already familiarized because we have already used that in the previous homework. Okay. So here are some streaming parallelism. You just use a CUDA stream, whatever. So this is some fancy techniques. I don't think you need it, but you should think about for the CUDA every time you execute kernel, right? But how to make the kernel execution like a streaming style. The CUDA provide you some provide you some function. For example, here CUDA streaming create. You can create a stream of computation, right? You don't want to wait for the first kernel finished and then to execute another ones. You want them to be a streaming style, right? Then that means you need to have some asynchronized, some setup here, but this is not the focus of this class. Okay. So let's try to summarize this deck of the slides. So first, we introduce the GPU architecture. The main difference between GPU and CPU architecture design, the GPU architecture is mainly optimized for throughput, but CPU is for the latency, right? And we introduced the CUDA programming. And yeah, just as mentioned several times, don't forget CUDA memory copy, right? You need to move the data back and forth. Sometimes after you finish the kernel, you don't observe any error. Maybe you just miss moving the data back to the CPU, right? So don't forget about the CUDA memory copy. And then we introduce the CUDA memory system. There is a global memory versus shared memory. Then finally, we introduce some of the GPU parallel library. Okay, CUBLAS and QFFT, some basic operations here. So for the global memory and shared memory, two important points you need to understand. One is memory coalescing, right? Another is for the memory bank conflict, shared memory bank conflict. And for the GPU, for the divergence, for the warp concept, you need to remember warp divergence. So these 3 or 4 concepts will be always repeated in your maybe future if you discuss with other people about the GPU programming optimization. Okay, so that's this slide. I want to quickly go through the DGEMM GPU version. And I think that's it for the whole semester. Okay, and let's try to go through the matrix application for GPU. So here is a GPU memory architecture, right? I show it several times. In the future, if you see this figure, you should immediately realize, okay, this is the GPU architecture, right? So we have the global memory shared by, I just try to repeat it again, okay? And just have several different stream multiprocessor, and they shared the global memory and the L2 cache. And each stream multiprocessor, there is a shared memory and L1 cache. And there is a warp scheduling to schedule different warps within each SM, and each thread block would be executed in one stream multiprocessor. That's a general idea, right? You try to summarize the GPU architecture and program in several sentences. So the idea of how to execute, how to implement a high performance GPU matrix application is you try to reuse the global memory data in shared memory, okay? So each input element is read by a width of a group of threads, right? And load each element into a shared memory and have several threads to use a local version to reduce the memory bandwidth. We usually call it a tiled algorithm. So this is something we have already mentioned that, right? So how you can use a shared memory, you just allocate a shared memory in a kernel, and you just have the sub block of the float, right? And each time you add something into the subblock and you do a synchronization and you accumulate the final result. Okay, so let's look at the matrix multiplication. So block inversion of matrix multiplication, everyone should be very, very familiar with that, right? We mentioned that many times in this class. And for each element for C, right? So it is calculated based on, for each element in C, it calculated based on one row times one column. So if I do the block version, this block of the data would be calculated based on this block of the row and this block of the columns, right? So this is a similar, this is exactly the blocking version of the matrix multiplication. So first we set the results to 0, and for each pair of blocks, we copy the data, do partial sum, and add the result of the partial sum to total, right? But let's see some detail. This is the blocking version. I don't want to show this, but okay, let's see this one. So if I want to calculate one element in matrix C, right? And I have the first block in A and first block in B, right? I calculate the one row times one column. Okay, and then I move forward, I calculate one row times one column and accumulate this value to C, right? So you can see C is not changed, the position of C is not changing. We just move the row and move the column and calculate the partial column times partial row and accumulate the result to C, right? And then we move to another, and then we move to another. After we finish that, we finish a one row times one column, right? And we get the value of C. So that's the general idea. Okay, and I think we calculate the cache miss or whatever also use this idea. So everyone should know that because most of you have a good grade in the midterm, right? So I don't think you will be confused for this. And what about the GPU? How we should use the GPU based on this algorithm? So the thread block, we can think about this is a thread block, okay? So each time you will ask a thread block to execute this block times this block, okay? And the thread block loops over blocks in blue and yellow matrix. Okay, you can think about this is a 2D thread block. And you can calculate the upper left corner to the right lower corner, right? So you have the order. And you load the data to the shared memory, and in the shared memory, you do the calculation. Okay, so one thread is still responsible for one element. So in one thread block, okay, in the kernel. And then you add the partial sum to the final result and get the value of the C. So if we look at this kernel part, it's not difficult, okay? And we usually call it blocked or tiled matrix multiplication kernel. Okay, so you can define a matrix multiplication kernel for the global function, right? So for global function means that this function can be called from the host, right? And at the beginning, you just define the shared memory variable, right? So this is the thing, I remember I mentioned before, so you are trying to control the size of the shared memory. It's similar to you want to use the maximum block size in cache, right? I ask you to, in the project 1, right, or project 2, I ask you to play with a different block number. That's for the GPU. Here is the same thing. You need to play the different number of a different size of the tiled of thread block for the shared memory, because shared memory is similar to the L1 or L2 cache in the CPU, right? So you have to play with the tile width to make sure that you fully utilize the shared memory, okay? So, but the problem is that if this size exceeds the shared memory size, that will cause some problem. So you should be care about the tile width here, okay? So tile width means the size of this block. Okay, and then you just calculate the ID, calculate the row of the element you want to work on, and then you just loop over the first and the second tiles required to compute the PD element, right? So you just loop all the, so here, for example, M, so in this example, M is from 0 to 3, right? We have 4 iterations. So in each iteration, you just calculate one block. Okay, so in each iteration, you calculate, you first load the data into the shared memory and do the synchronization, and you calculate the one tiled row times one tiled column, and then you do another synchronization. After all the loops, you just put, so after this loop, that means you finish the one row times one column. You just put the data back to the global memory. And for this step, you just accumulate in the shared memory, okay? So try to be clear within, so I just want to try to repeat. So this final step is copy the data from the shared memory to global memory. This is the final result for C, one element C, okay? Within this loop, you just accumulate the data in the shared memory, okay? But every time you finish the computation for all the threads, you just need to have a synchronization, right? And this is a step to accumulate all the results in one column and one row. Okay, this is a first version of how to utilize the shared memory. We have some other further blocking to increase the performance, but generally speaking, this is the idea of the shared memory. You just load the data to a shared memory and calculate in the shared memory and accumulate the result in the shared memory, and finally write the shared memory data back to the global memory. Okay, the reason is that the whole block, a whole thread block load into the shared memory could be used for multiple times, right? That's the idea. You load the data one time, but you keep using that in the shared memory. Okay, so that's the general idea of how you utilize the shared memory. I mean, it's similar to CPU, but for CPU you don't have this control, right? You just play with the cache size and ask the CPU to reuse the data in cache. But here you have a specific control. You use a shared memory as a caching, and how you operate in the shared memory, right? It's like shared memory is a cache between the global memory and the GPU processor, right? But you can specifically control how you operate that. But because you have this control, you should be pay attention, right? This is your control, not the system control. So you have to be pay attention when and where you should put a synchronization. So for example, you load the data. After you load in the data, definitely you need to have a synchronization. So we don't have a loop to load the data. What's the reason? Because we set all the elements with the thread, right? So that means each thread just load one element to the shared memory and do a synchronization, okay? For this block and this block, let's see how for this block, right? We have the 16 times 16. This is 16 times 16. We have the 1256 threads here and 256 threads here in a block, okay? Here to load the data. And after load the data, just do a synchronization and ask each thread to calculate its intermediate data and accumulate it to the global value. Okay, not to global, to the value in the shared memory. And finally, you just copy the data back. So this is the idea, and I think in your final project, at least you need to implement this algorithm. I manually ignore some detail here. You just need to put the indexing calculation and some other things here, right? I don't think I have already given you all the computation here. You just need to figure out the indexing calculation here and test and benchmark and compare with the CUDA. Okay, so here is something related to the tile size or tile width. right? So the block size is a tile width, as I mentioned, right? So this is for this gray block, right? It's a tile width times tile width, and the grid is width divided by tile width, right? For example, this matrix is a 1024. If I said 200, if the matrix the n, for example, is a 128, if I said 16 here, right? You can launch the thread block, each thread block with 256 threads, and how many block threads? It's 8 times 8, right? 64 thread blocks, right? But this is a very small matrix. If you have larger matrix, as I mentioned, you need to make the streaming multiprocessor as busy as possible, okay? So the first order size consideration in GPU. Yeah, so this is what I just mentioned. So if you have the 16 of the tile width, you will have the 256 threads. If I have the, for example, if I have the 166 times 66 thread blocks, then you would have 4,000, more than 4,000 thread blocks. Okay, and as I mentioned, these 4,000 thread blocks would be executed in the different streaming multiprocessor. Okay, you can think about each thread block perform 2 times 256 is about 512 float loads from global memory. Okay, and there is how many multiplication and addition here. So memory bandwidth is no longer a limiting factor. You can calculate something here, right? So that means you try to use a shared memory efficiently and avoid the memory bandwidth for the matrix matching application. Okay. So here, because the G8080 only has 16 shared memory, so the 16 is using 2 KB, right? But as I mentioned, if you are using the V100, you should accordingly calculate the tile width you can use, right? So for example, this is a 2 KB. If I assume K80 has 16 KB, that means I can increase the width by another 2. So with another 2, it's 2 times 4 is 8 KB. It's still fine. But if I increase by 4, the shared memory is not enough, right? So here's something you need to think about. For the V100, I can tell you it's a 48 KB, or you can use a dynamic allocation to use up to 96. And how you can use up to 96 and how many threads for one block. You just think about that, right? So this is something you need to play with in your final project report, right? You try different tile widths after you use a tile width as a variable in your code, okay? So you can see here, if you set the tile width at 32 and you will use the 8 KB. So if we consider there is 16 KB shared memory, they are allowing only up to 2 thread block actively executing at the same time, okay? So maybe you can use all the shared memory, but you can only execute 1 thread block. So you need to play with the number and see which one is better, okay? So here are some calculation for the bandwidth, right? You can calculate based on this 86 gigabytes per second bandwidth, how much performance you can get, right? After you analyze the theoretical performance, you can compare with your practical performance. You know how to calculate the G flops, right? We had a question in the exam 1. 2n cubic divided by the time, right? You can calculate the real G flops. You can compare the maximum supported G flops and your real G flops. That is something you can mention in your report to make your report better, right? So here is a tiling size effect, not tiled with different size, and based on different architecture, definitely this figure would be different, right? And I'm interested to see what is a figure in our V100 GPU. So for example, if I write the report, I will test on different tile size, right? I compare with the no tile version, and I compare with CUDA, and I can see what is the performance improvement compared with the baseline, and what is the performance gap between the optimal one, right? Generally speaking, you can have this figure in your final report. And I have already provided you some code. And you just need to fill out all the code and make it comparable, compilable and run with the CUDA. Okay, I don't think this is a very difficult project, but should be very, very interesting based on my understanding. And I provide you some test data set. You just need to load the data set. I think the data set is binary. You just use the binary open in C or C++ to open the data, and it has some specific format. For example, the first 2 or 3 element would be a size or whatever. You just follow the instruction for the format, and you can load the data. Okay, I think that's it for the quick overview of the tiled version of the metric application or block version. And it shouldn't be difficult. And this is all the thing you need to finish before the end of this semester. Okay, that's the only thing we left. And I will post the project, the project 5, right? OpenMP, yeah, OpenMP project. Yes, I will post the grade as soon as possible. I try to post it before the 24th, right? I just finished the midterm grading, and I will post the project file as soon as possible. So for example, if you I mean, based on the current score, you think, okay, you are fine, and you are fine. But if you don't know if you are fine, and you still need to think about the project 5 score and the final project score, just send me an email. We can discuss, right? Because if you want to make a decision or PNF or final grade, you're welcome to let me know, right? So yeah, I think that's a lecture content for this semester. If you have any question before we close, before we wrap up, before we close this semester, any question we can discuss here?
I just had 2 quick questions.
Okay.
For the both on the final project. The first one is in the matrix data files, the first 2 numbers, the numbers come in like row then column size, right?
Yes, I think so. You check, but the matrix I give you should be a square matrix, right?
All right. And then does all this, are we using flat 2D matrices for this project?
2D, you mean, what do you mean by 2D matrix? Matrix is always 2D, right?
Oh, I'm sorry. But like just like with one, like make it flat so there's only like 1 index instead of using 2 indexes.
You mean when you want to launch the GPU kernel, you want to use a 1D or 2D? This is your question?
Yeah.
I think depends on you. If I were you, I would use a 2D because 2D is easy to, for example, here, right? We have the code. 2D is easy to map the, the index and the data, right? But if you want to use a 1D, it's fine, right? But you need to manually convert the index between 1D and 2D. So for example, here you use 2D, that will help you to reduce a lot of, index calculation, right?
Right. I just didn't know if like that pre-built function we're using, the CUDA one, I didn't know if that needed like a flatter.
Yes. That need a flat array, right? And actually, yes, your point is right. CUDA needs to have a flat array. And for example, you can just allocate 2D pointer, right? And you pass the first pointer to the CUDA, and it's actually the flat array. But I mean, yeah, it's based on you. If you want to convert to 1D or 2D, you can do that. Yeah.
All right, thank you.
So any other question?
Can you please post the Zoom lecture from last Thursday?
Lecture or video?
The video.
Oh, definitely. Yes, I'm uploading the video today with this lecture video together.
Thank you.
Yep. Okay, so yeah. If you have any question, just feel free to send me email or we can do a Zoom meeting. And I'm trying to respond as soon as possible. Even I have several deadlines, but I tried my best to reply. For example, before the decision, right? You want to make before the 24th, and for the final project, yeah, I don't think it's very difficult. So try to finish as soon as possible, and we can post the final grade maybe very soon after you submit the project, because some students, if they need to have a grade, we need to grade for them, right? The ABCD if they want. And I think that's it for this semester. I really appreciate you attending the cluster, even if in the special case, right? Still, we have more than about 15 students to keep attending the class until the end. And hope you can learn something for the parallel computing and HPC, right? And in the future, if you find a job or do a PhD, GPU or OpenMP or MPI will help you to improve a lot of things, for especially for the performance, right? So that's a thing I think is maybe important for you. Okay, so yes, I encourage a student to take the survey for the class. For example, any comments, any question, or not question, any comments or suggestion for me to improve the class in the future. Yeah, just welcome to put the comments, because every class will have the survey, right? In the future, in later. Okay, so that's it. Thank you so much for everyone, and yeah, hope you have good time, and take care and stay safe. Okay, thank you.